All right. For 11.5, we're finding the absolute max or the absolute minimum. And so far, what we've been doing is just the local max or min. And now a local max or min, excuse me, could be your absolute max or min, right? Like if I have a parabola, that is the only graph, and that is an absolute max. There's no graph above it. But we have other graphs that go wiggle and turn and do all sorts of things. So we have to be able to find what is an absolute max. And then in the next section, we will use this idea in business and see why we've been learning it. Okay, so the first idea here is absolute max and min is where all values at a certain number x are greater than every single other value. Okay. For an absolute min, it's less than. So basically, it's the lowest absolute point on your graph or the highest. That's all that's trying to tell you there. And then here are the theorems. A function that is continuous on a closed interval has both an absolute max and an absolute min, for sure. So if I say I want to look at my graph from here to here, you have stopping points here and here. So you have to have a low point and a high point. If it continues forever, you might not have a low point and only have a high point, or vice versa. Okay, so this is important. If we have an interval, we absolutely have a max and a min, absolute both. Theorem 2, absolute extrema, if they exist, must only occur at critical values or endpoints. We already know how to find our critical values. That's where the derivative equals 0, or endpoints. So if you have endpoints, those could be your absolute max or min as well. So what do we have to look at? Critical values. What else do we have to look at? Endpoints. That's the main idea. Okay, the second derivative can be used to decide if something is an absolute min or max. So we find the second derivative, we put the value in. So if it's at 2, we're looking at this number 2, it's an absolute min, or we think it is. Excuse me, you could put that into the second derivative. If it's positive, it's an absolute min. If it's negative, it's an absolute max. So we can use the second derivative to help us. Okay, so here's the procedures. It says start with making sure it's continuous. Start with the critical value. Okay, where's the critical values on the interval given, or where are the critical values in general, and then look at the endpoints, decide what is the max and min. So let's do some problems. That'll help us. So this first problem here, what we're going to do is find the absolute max and min. Now this has endpoints from -2 to 5. So that means we have to have an absolute max and min. So where do we want to start? We want to start with our critical values. And the critical values can be found by finding where the derivative equals 0. So what's our derivative? Okay, well, the first derivative is 14x minus 14. Okay, where does this happen to equal 0? Well, we'd add that 14 over, divide, and I get 1. 14 divided by 14 is 1. So we have a critical value at 1. So that could be an absolute max or min. Now, I am a little lazy. I don't want to do increasing, decreasing, and all of that to see if it, and do a sign chart to see if it's going from positive to negative. So what I'm going to do from here is I'm going to make a chart that has our x values and our functions values. So bear with me for a sec. We know our critical values at 1, and we have 2 endpoints, -2 and 5. And what I do is I plug these into the original function. That's why it says f of x. And I see what is the value. Okay. Is that value the highest point, lowest point? So I would have 7, 1 squared minus 14 times 1 plus 5. So if I put that all in, I get 1 squared 7, 7 minus 14 is -7, plus 5, I got -2. Okay, the next value is an endpoint. Okay, so the graph is doing something and you have an end point there. Well, it's an x squared, so traditional, sorry, this way. And you'll have an end point. All right, so we will put that -2 into the function as well, the original. And with this one, I get 61. Okay, same thing for the last one, 7, 5 squared minus 14, 5 plus 5 is 110. So we've looked at our critical values and we've looked at all of the endpoints. Which one is the highest value? 110. Which one is the lowest value? -2. So we have an absolute minimum at x equals 1 and the y equals, if we wanted the y, -2. And the absolute max is at x equals 5 and the y value is a 110. You don't always have, sometimes it just says the x value, like all the other problems we've been doing. It doesn't always say the y, but there you go. Now, I didn't use a second derivative at all. I could use the second derivative and find it, first of all. And the second derivative of this is just 14. So it's just positive 14. So yeah, it's not helpful at all. So it'd be always greater than 0. So I would only use the test for second derivative if you don't have endpoints. Because if I did not have the -2 and 5, the second derivative would be 14, and it would tell me that you only have an absolute, it's greater than 0, right? So beep, 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 beep. You only have an absolute minimum. Greater than 0, absolute minimum, because it's just 14, so it's always greater than 0. There is no absolute max because the graph goes like this if we didn't have endpoints. Okay, let's sketch a little graph of this just to kind of help. So I'm going to bounce into Desmos, show you kind of pretty without just looking at my chicken scratch, but 7x squared minus 14x plus 5. Here we go. Here's our, oops. How did I do that? Plus 5. Here's our graph right here. And on this graph, we can see the absolute minimum is at 1, -2, which we've already seen that. And so if we didn't have endpoints, we could look at it and see that absolute min. We do say we want x. I don't remember. Let me see if I remember how to do this. X. I don't know if I remember how to do this or not. Let me delete that. So what was it between -2 less than or equal to x, which is less than or equal to 5. And that's not the prettiest way, but it's the only way I could think of right now. So let me go up a little here where this cuts it off. It's not just a little, there we go. Here is at that 61, right? Because the green is the only section I want. And the other one was at what, 110. So up here is at the 110. So only the section that's green do we want. So you can visualize that there would be a line cutting that off, right at both sides. Okay, so that's kind of helpful. You can look at it and you can find where the end crosses. I think there's another way to do it in Desmos, but that's the only way you can think of. All right, let's look at another one. So problem 2 now says 5x to the third minus 6x to the fourth, and it does not say any endpoints. So we might not have an absolute max or min because we don't have any endpoints. So we start with, okay, well, what's the derivative? Okay, well, the first derivative is going to be 15x squared minus 6 times 4 is 24x to the third. Okay, and I am going to do the second derivative as well because I want to use it because there's no endpoints. That's going to give me 30x minus 72, right? Yeah, okay. Yeah, it took me a minute. It's all right. I do it in my head like 2, 4, 6, right? 3 of those, and then 4 times there's 12, and then 6 equals 4. Yeah. Woo. When I'm making this video right now, I have been sick for like 3 weeks, or 2.5. All right, so we have to start with that critical value. So that's where the derivative equals 0. So 15x squared minus 24x to the third. Where does that equal 0? We have to use our factoring rules. So I'm going to take an x squared out. I could take a 3 out too. I don't know that it matters, though. We'll just do an x squared because I know minus 24x equals 0. So we just took that square out of the 15 and we were left with one of them with the x to the third. And then where does each of these individually equal 0? So where does x squared equal 0? At 0. Anytime I pull out any x's, gives me one solution of 0. Then we look at 15 minus 24x. Where does that equal 0? We will minus the 15 over, divide by the negative 24. So minus the 15 over, divide by the negative 24. They're both negative. So I get 5/8. Okay, you'll get 5/8 whether you take the 3 out from right here, if you see it or not. So we still get the same answer either way. So we have 2 critical values, 0 and 5/8. So we can then make our little chart, right, of our x values and our y values of our original function, which is the 5x to the 3 minus 6x to the fourth. So our x values we're going to plug in are 0 and 5/8. So if I plug in the 0, I get 0. Yeah, because 0 times anything is 0, and so 0 minus 0 is 0. If I put in the 5/8, I'm going to cheat. I did it on my calculator. I got 625 over 2048. I just used that fraction key. So 5 times 5/8 to the third minus 6 times 5/8 to the fourth. It'll give you a decimal. Click math, then fraction, and it'll do that part for you. Okay, so those are our 2 values we got by putting them in. And then what we could do is use that second derivative to check. This one is definitely, the 0 is definitely our low one. And this one is definitely our higher one, but we're going to do the second derivative check. Okay, so I'll take the second derivative and I will put into the second derivative the 0 for x, and that would give me 30 times 0 minus 72 times 0 is 0. So if we go back, we got 0 for our second derivative check. So if we go back to the original, it can't be equal to 0, or it is not. If it equals 0, yeah, no, it can't equal 0. I looked at the equal 0. That is the first derivative. So then I had to read the whole thing and remember how it went. So we have 0. So that is not an absolute max or a min. Cool. So we can't tell. It fails. I don't know how to say that. Fails the rule. So then what we're going to do is we're going to do the second derivative of 5/8. And that's still going to be like 30 times, I wrote the 30 weird, 30 times 5/8 minus 72 times 5/8 squared. See, I should have a square there. I was like, it had something else. 5/8 squared. Okay, I get negative. I don't really care what it is. It's negative 75 over 8. So a negative. Let's go up and see what that tells me. So from here on our rule is if you're less than 0, it is a maximum. Okay, absolute maximum. So we have no absolute min and we only have an absolute maximum. So I'm going to cross that out for a second. So we can write out our final answer. There is no absolute minimum. Okay, there was the second derivative at both critical values was not greater than 0. It was less than 0. If it's greater than 0, then we have an absolute min at that spot. We didn't. So we have an absolute max at x equals 5/8 and y equals that weird number 625 over 2048. Okay, kind of weird. Let's graph this. Okay, the original was 5x to the third minus 6x to the fourth. There's our original graph. Oops, I'm like way up there. Okay, here's our original graph. And now I can see that we had 0. If it'll let me push now, it's not going to let me. So we have that 0 right there. That is it. I mean, it gave us a lower value, but that second derivative failed and said, but it's not. So that's why the second derivative is important when you don't have endpoints. And then this value up here that we have the 5/8, which if you do 5 divided by 8 and actually do the decimals, you're going to get that answer. So 5/8 is 6.25, and then 0.3-ish is the other number, the y value we found. But that is your absolute max, and you can see that there's no higher value, but you can also see it goes on forever. So there's no min, no absolute min at all. So the second derivative part is kind of helpful to look at and let you know whether or not that value is working for you. Okay, so let's move on. Problem 4. Where's 3? Oh, I crossed it. Hold on a second. Watch this. Fancy moves. I'll just erase a little bit of this. Doesn't matter. You have it on your notes. You can pause the video and get that part of the notes. Okay, here's our second problem here. I like this one too because the rational expressions kind of throw people for a loop a little. So when we start to do the first derivative, oh, we better remember our quotient rule. So the quotient rule says denominator, original, times the derivative of the top, which is 2x, minus the original top times the derivative of the bottom, which is 2x, all over the bottom squared. Can we say yuck? Yes, we can. Where does this thing equal 0? Goodness, So we do want to simplify this to be able to do the second derivative. And I'll just simplify it while we set it equal to 0 or whatever. We'll get it. We'll get there. So 0 for critical values. We'll have the 2x times through here. So 2x to the third plus 4x minus this entire thing. 2x times x squared is 2x to the third. 2x times -5 is -10x. And then we have to remember to minus that whole thing off. So one more step to get that top. This would become positive, that becomes negative, that becomes positive. And then we could add our like terms. Oh, the 2x has disappeared to the thirds. That's nice. 4 and 14, 4 and 10 make 14. 14x on the top over x squared plus 2 squared. Okay, great. That's simplified a lot prettier. So this is our final derivative, and we have to set it equal to 0. So what happens to this bottom part? It times up to the 0, right? This times 0 is 0. So we basically are solving 0 equals 14x. Divide the 14 over and you just get 0. So we have one critical value at 0. Now, if we went to do the second derivative, we would do that of this simplified version right here. So again, original top, x squared plus 2 squared times the derivative of the top is 14 minus the original top, 14x. Oh, kind of running out of room here. And then the derivative of the bottom is a chain rule. So I bring the 2 out front, okay, 2 out front, and then you keep everything the same, x squared plus 2, and drop 1 on the exponent here, but then you have to times it by the derivative. Let me rewrite this real quick. Times it by the derivative of the inside. We need room for this so you can see it. It's ugly. So I'm bringing the 2 down out front, keeping everything the same, bringing that to a 1. So that's the big picture, right? 2 comes down, drop 1, keep everything the same, but I have to times it by the derivative of the inside. The derivative of the inside is 2x. Okay, from the 2 going down front, and then that one goes away. All right, all over the bottom squared. Well, so then that's going to give us x squared plus 2 squared squared. And you could times those exponents to do the fourth. That's totally fine. We don't need to simplify this one though, because we'll just be putting in values to see if it's greater than 0 or less than 0. So that's nice. We're just putting in values. So let's go ahead and do our value. If I put into the original function my critical value of 0, I get out -5/2. So this is my point I'm looking at, 0, -5/2. That's our only point because we had one critical value. Then from there, I need to put that 0 into this derivative here, the second derivative. So this is the second derivative of the 0. So if I put a 0 here, 0 squared is 0 plus 2 is 2. So this is going to give me 2 squared times that 14 minus, now put in the 0 here, right? And here, this would be 0, 0 times anything is 0. How did I get a 4? This times is 0. I don't know how I would have got a 4 because this would be 0 times this as well. 0, 0, 0. I don't know. I must have just wrote a wrong number down. This has to be a 0 there. Okay, all divided by 0 squared plus 2 is 2. So 2 to the 4th. I don't know. I always have to sticky note when I find something that I did wrong. I'm like, fix. To make fun of me later. I see what what I did on mine was somehow I had a number here and I forgot to square the square on the second derivative. So who knows? Anyway, what does this give us? Well, 2 squared times 14 is 4 times 14. And then we're going to divide that by 2 to the 4th, which gives me 1.75. So 1.75, is that bigger than 0 or less than 0? Okay, that is going to be bigger than 0, 1.75. So it has to be an absolute min. Let me scroll back up and remind you on our notes, it's bigger than 0. It's not at 0, which is good. So then it's an absolute min. Where was I? Here, problem. Here we are. So we have an absolute minimum at x equals 0, and the y was -5/2 if we cared, and no absolute max. And if we get one critical value, we have a min or a max. Like, there's no way around it. Okay, let's take a quick look at the graph of this one, because I always think we should look at the graphs to see and relate them. This was a division, and we have x squared minus 5 on the, and I'll fix that. It was x squared plus 2 at the bottom, right? Yep, and then I gotta add the -5 up top. There we go. That's what it looks like for our graph. So I can definitely see right here at 0 that I have an absolute minimum. And then it looks like both sides just keep getting bigger and bigger in both directions. So I have that absolute min, and that was it. And that's what we said, was we had an absolute min at that point. So perfect. Here's our absolute min. All right. So 0. Okay, so let's do a couple more of these. I was like debating if I wanted to do, because which one? I want to make sure that sometimes they do just 2 easy ones with 7/x. Is that one that I want to do? Or I don't know if I'm going to do that one or this one. This one's too easy. What's the last one? Does it have an E? Okay, fine. Let's do the only one that has a little bit of trick to it is this one. So we'll do one more with this one because it has that 7/x. So it does make it a little tricky. So let's go ahead and start with our derivative. And I do want you to notice that this one has an interval of 0 to -infinity. Okay, so let's start with the derivative. And we'll do each term. So 6 disappears, we get that 2. And we could rewrite this as 7x to the -1 because it's just a number on top. If you did the product rule on that one, you could get the same answer, but you don't have to because it's easier to think of as a -1, but either way. Then the -1 times the 7 is -7x to the -2. And that's our first derivative. Okay, then where does this equal 0? Oh, right. I think we might want to look at this like this. That might come over a little easier for you. It's hard to think about how would I get rid of a negative 2. You can't take a negative 2 root, so it's a little weird. All right, so then from here, I'm going to minus the 2 over, so it becomes negative 7x squared equals negative 2. Okay, then I'm going to times the x squared over, and I get negative 7 equals negative 2x squared. Then I'm kind of going then now back the other way. Then I could divide by the negative 2 on both sides, and I get 7/2 equals x squared. And we know then we would have 2 solutions, negative and positive square root of 7/2. So what is the square root of 7/2? So square root of 7/2 is about 1.87. So our answer is the positive and negative square root of 7/2. Okay, and that equals x. I'll leave it 7/2, but I want us to know that this is about positive or negative 1.87. Okay. All right, so second derivative. We have 2 values here. We also have 0. Could we include 0? No. Just kidding. We can't include 0. If it would have been a square bracket, then that's an endpoint. We can include 0. We can't on this one. So we don't include that. So if we go down here, are either of these numbers less than 0? Yes. So negative 1.87 is not in domain, or your range of values that you were given. So we only look at x equals 1.87. And so it's either the absolute max or the min, right? And we don't have the other one. So if we do the second derivative of this one, pretty basic one, thank goodness, the 2 disappears. Negative 2 times negative 7 is 14x to the negative 3rd power. Ew. Now, all we're doing to the second derivative is putting in the value that we got. You could totally use the decimal because we're just seeing about, we really care if it's positive or negative. So this ends up being about 2.14, so it's positive. What did we say if x was greater than 0 in the second derivative? Was it a min or a max? Go up and look. It's an absolute. Greater than 0 is an absolute min. Okay, so we have a minimum. Right. So we have an absolute minimum at x equals 1.87. You could find the y by putting that value in. Sometimes I think because this is like absolute max and min, it's kind of a point, they probably will ask for the y value. There you go. All right, I'm going to stop there. So absolute max and min, if there's endpoints, square brackets, you have to also include those ones. A lot of them only have one critical value that you're looking at. But if you have more than one, then you have to look at, the y values to decide which one's bigger or not. So if we just go up to this first problem we did, we had to check all 3 of these to see which one had the highest and the lowest. We do that if we're given the endpoints. All right. If you're not given endpoints, you can only consider the critical value, which would just have been this one. Okay. So like this one here, we only had a critical value of 0 and 5/8. So we had 2 critical values, so we had to put those in and get the y's. 0 is definitely smaller, but it failed our second derivative test. I erased that part. So it failed the second derivative test, so it couldn't be. So this one was our only one, and it was a minimum. All right. Hopefully that's helpful.